Hi, my name is Reddy, and I'd like to present our recent work on training flexible and adaptive user interfaces. We aim to help users with disabilities type without a keyboard using alternative inputs like eye gaze recorded by a webcam or neural activity measured by a brain implant. The challenge is to infer the user's desired word or character from these different kinds of user inputs. We set up an eye gaze based system based on prior work that presents a set of words to the user, waits for the user to look at their desired word, then takes a picture of the user's eyes through their webcam. Given this webcam image, the interface then predicts which word the user wants to type. Our algorithm is agnostic to the type of user input it receives, so we can replace the eye gaze input from the webcam with other kinds of input instead, like recordings from an electrocorticography or ECOG-based brain-computer interface. This hardware is surgically implanted inside the user and provides us with 128 channels of input. In this case, the user's input is their brain activity as they look at the display and think about their desired word. The standard approach to calibrating this interface with supervised learning requires a new user to provide paired data of inputs and actions, but this can be time-consuming and disruptive. Our insight is that instead of calibration, we can initialize the system with the default interface that's designed for an average user, then quickly customize the interface to a new user by observing them type. As the new user types, we treat that user's backspaces as naturally occurring feedback on the accuracy of the interface's actions, and train the interface online through this reinforcement. Our method for learning from backspaces is simple. We present the set of words to the user, take a picture of the user's eyes through their webcam, then feed this input to our selection policy. We sample an action from this policy. The user sees this action, compares it to their desired action in their head, then decides whether or not to backspace. This decision to backspace naturally provides our system with feedback that it can use to derive a reward signal and train the policy through reinforcement. In particular, we train a reward model to be a binary classifier that predicts the likelihood of this backspace. What that lets us do is treat the system's default non-adaptive interface as a prior policy, and use the backspace likelihood model to update that prior to a posterior policy. And we call this method X2Text, or X2T. X2T doesn't make any assumptions about the type of user input, so in addition to conducting experiments where users provided eye gaze input through a webcam, we also conducted a pilot study with one user who used an ECOG brain-computer interface to provide input to the system. We evaluated X2T primarily through a user study with 12 participants who used their eye gaze to type, and found that learning a reward model from online user feedback substantially improved the performance of the default non-adaptive interface, and that users for whom the default interface performed particularly poorly tended to benefit more from this online training. Qualitatively, X2T was able to save the default interface from making incorrect predictions by ignoring the default interface's incorrect 2D gaze position estimates, and instead training a separate end-to-end reward model that directly predicts actions. Here we plot the default interface's 2D gaze position estimates given user inputs intended to select the bottommost button on the screen. The gray circles indicate cases where the default interface predicted the correct action, while the orange circles indicate examples where the default interface predicted the wrong action, but the reward model managed to correct it. The widely scattered 2D estimates show that action prediction is actually quite hard for this button, perhaps because the user's eyes tend to be more obscured when they're looking down. By training a reward model and user feedback, X2T helps the interface recover from these incorrect gaze estimates. We ran a pilot study with one participant who used an ECOG brain-computer interface to provide inputs, and found that X2T performed substantially better than a default interface. Interestingly, the default interface never predicts the topmost button action, leading to a 0% recall rate for that action. And this is most likely due to changes in the feature processing pipeline or other kinds of distributional shift in the user inputs over time. In contrast, though, X2T achieves over 70% recall on the topmost button action, suggesting that it can overcome some of these challenges. Thanks for listening. Here's a link to our project website.